What we'll look at here now is some word problems and applying the law of sines or cosines to them. As we've worked with word problems before, obviously the key is drawing the diagram, so we have to go through it piece by piece and put together our diagram. Then we also have to be able to choose, in this case, whether we're going to use a law of sines or law of cosines based on the information presented and placed into our diagram. So as we've talked about before, I'm going to read through the entire equation, then go back through it line by line to put my diagram together. Two ranger stations are located on the east-west line, 110 miles apart. Forest fire is located on a bearing of north 42 degrees east from the western station at A, and a bearing of north 15 degrees east from the eastern station at B. To the nearest 10 miles, how far is the fire from the western station? So we'll start out here by trying to sketch our diagram. Our first statement, two ranger stations are an east-west line 100 miles apart. Let's try that again. Go triangle a little bit straighter across here for an east-west line. So our two ranger stations are 110 miles apart on an east-west line. Our next statement says a forest fire is located on a bearing of north 42 degrees east from the western station at A. So our western station is A, and we're going to go north 42 degrees to the east, and over this direction is where our forest fire is going to be located. I'm just going to leave it unmarked for now, but I've drawn in the north 42 degrees east into our sketch here. So let me just try that one more time. 42 degrees. All right then, next statement, a bearing of north 15 degrees east from the western station. So from our western station, we're going to go north. First of all, it's station B, north 15 degrees to the east. And our 15 degrees is this little angle right here. And our forest fire then is located over here. Filling in a little bit more information here. I guess that's it. To the nearest 10 miles, how far is the east fire from the western station? So we're trying to find this value right here. As we look at our triangle, a couple things to note, or one big thing to note, I guess, is this is a north-south line right over here, and this is an east-west line. So if this is 42, this angle in here is complementary. It is 48 degrees. And then if this angle here is 15 degrees, this is a north line. I have a right angle here, so this entire angle for our triangle is 105 degrees. So now, if we notice, we have two of our three angles. If one angle is 48 and one is 105, those total would be 153. That means this angle here is what adds up to be 180, or it'll be 27 degrees. So now that we have all three angles in a side, we can use our law of sines, because 110 is across or opposite the 27 degree angle. So there's one of our ratios, 110 over the sine of 27. We're trying to find side x, and the angle opposite it is 105 degrees. So then we can cross multiply, and we can have x times the sine of 27 equals 110 times the sine of 105. And we could go ahead and divide by the sine of 27. And if we divide by the sine of 27, we're going to get x to equal about 234 miles away. Okay, so let's move on here to our next problem. And you can see as we read through this, standing on the bank of a river flowing north, Mark notices a tree on the opposite bank at a bearing of 115.45 degrees. Lise is on the same bank as Mark, but 428.3 meters away. She notices the bearing of the tree is 45.47 degrees. The two banks are parallel. What is the distance across the river? So let's just start out and make our river flowing north. So we'll draw straight up and down here for our river. And just randomly somewhere over here, we'll put Mark. Mark measures his angle to the tree on the other side of the river as 115.45 degrees. So our bearing is always measured from a north line in a clockwise direction, so 115 degrees would come over in this direction somewhere. So we're going to put the tree on this side over here. Here's our tree. Next statement. Lisa is on the same bank as Mark, but 428.3 meters away. Now here's one of the reasons we read through the entire equation or statement first, because she could be above him or below him, but because her angle is 45.47 degrees, Lisa is going to be down this direction. So she's 428.3 meters away, and Lisa is here. Her bearing, measured from the north line in a clockwise direction, this angle right here is 45.47 degrees. The two banks are parallel. What is the distance across the river? So we're going to have to draw an altitude into this triangle. If we come straight across, this is going to be the distance we're looking for. So we're making an assumption here. We're saying Mark and Lisa on a north-south line. So the good news is with that assumption, we're going to say this is a right angle. I think that probably should have been spelled out better in the problem, but we'll go with that right angle. Basically, we're going to have to find one of these diagonal sides first. So as we move forward, if this angle up here is 115.45 degrees, we have a straight angle here. That means the angle inside the triangle right here is 64.55 degrees, 180 minus 115.45. So once again, we have two of our three angles, which means we can find our third angle. I'm going to label that angle up here is 69.98 degrees when I add 64.55 and 45.47 and subtract that from 180. That gives us our third angle here. So as we look, we're not going to solve for side X right off the bat. We're actually probably going to solve for one of these other two sides. So I'm going to solve for this side down here and call it Y. I set up my law of sines. I have Y over the angle opposite it, which is 115. I take that back. It is 64.55 degrees. 64.55 degrees. The one side that I do have is the 428.3, and it is opposite my 69.98 degree angle, so the sine is 69.98 degrees. I could cross multiply and solve here, so y times the sine of 69.98 degrees equals 428.3 times the sine of 69.98 degrees. Oops, how about 64.55 degrees? Just making all sorts of mistakes over here, not paying attention to what I'm doing. So 64.55 degrees. I'll divide by the sine of 69.98. And we'll get, I'm going to put the information up here, side y is about 411.61 meters. So now if we come back over here, I have a right triangle that I have the hypotenuse of because we just found that hypotenuse. So looking at what I'm trying to find the opposite side from this angle here, 45.47. I have the hypotenuse. So back to our right triangle trigonometry, the sine of 45.47 degrees equals the opposite side of x over our 411.61. And if I take and multiply both sides by 411.61, I'll be able to solve for x, and x is about 293.4 meters. So both of those problems included our bearings, two different ways of measuring bearings here. This one was from a north line in a clockwise direction. This one up here had our two directional measurements in it. Both of them measured from a north line and both in a clockwise direction because of the east. So let's move on to our next one. While building a ski lift, the surveyor measured the angle of elevation at the base of a 20-foot tower as 30 degrees. The angle of elevation at the top of the tower is 37 degrees. How far away was the base of the tower? Well, let's start here with a simple tower. We'll put a straight up and down line. Anytime we measure the height of something, it's a vertical height. So a 20-foot height. Our angle of elevation to the base was 20 degrees. So we're standing over here somewhere, and we'll go to the base of the tower, remembering our angle elevation is measured from a horizontal line. So this angle right here is 20 degrees. The angle of elevation then to the top of the tower was 37 degrees. So that from that same line up to our line of sight to the top of the tower is 37 degrees. And we want to find out how far we are away from the base of the tower. We'll go with the slant range distance there. If we fill in a little more, from here to here is 20, from here to here is 37. So the angle inside our, oops, that wasn't 20 degrees, it was 30 degrees. Got to be able to read here, 30 degrees. So the angle inside our triangle is 7 degrees. Now notice right off the bat we have the length of 20 over the angle, or opposite the angle, so over the sine of 7 degrees. Our law of sines, one ratio is filled out. So if I want to find x, I want to know the angle that's up here. A little bit of legwork to get to that. I'm going to extend this straight down and this straight across, which will make a right angle. So if this is 90 and this entire angle is 37, that angle sum all the way around the outside is 180. So 180 minus 90 is 90, and 90 minus 37 is 53 degrees. So we're going to label this angle right here as 53 degrees, and that will give me my law of sines set up. X times the sine of 7 degrees equals 20 times the sine of 53 degrees, and we'll solve for x, and x is going to be equal to about 131 feet. All right, so let's keep moving on here. Boat left the dock and sailed for 5 miles on a course of north 30 degrees west. The boat then turned to a course of south 15 degrees west and sailed for 10 miles. At this time, the navigator measured the angle back to the dock as north 50 degrees east. How far away is the dock? So here's our different measures of bearings, north and west, south and west, north and east. We'll just start with our first statement, boat left the dock. So randomly, I'm just going to label my dock right here. He sailed for 5 miles on a course of north 30 degrees west. So my course is north, and we're going 30 degrees to the west of that. So in this direction, and we'll label that as 5 miles. So angle here, 30 degrees. From here, once he sailed 5 miles, he changed to a course of south 20 degrees west. So from here, south, and we'll go 20 degrees to the west. He's traveling this way. This angle right here is 20 degrees. He sailed for 10 miles. So this distance is 10 miles. And then from here, he measured the angle back to the dock to be north 50 degrees east. So from here, we're going to go north and 50 degrees to the east to get back to the dock. So this entire angle right here is 50 degrees. Now keep in mind that's measured from our north line all the way over to here. It's not just the angle inside our triangle. I'm going to backtrack here. We have two sides. If we can find the angle between those two sides, we can use our law of cosines. So if I take a longer look here, I have a north-south line right here, and I have a north-south line right here, which means those two angles are parallel. This line then cuts through there as a transversal. My alternate interior angle tells me if this is 30, then this is also 30, or this entire angle right here is 20 plus 30, or 50 degrees. So as I just mentioned, we now have the angle between those two sides, or the angle opposite our x, which would allow us to use the law of cosines, and we could say x squared equals 5 squared plus 10 squared minus 2 times 5 times 10 times the cosine of 50 degrees. And if we plug that into our calculator, we're going to get x to be about 7.79 miles from the dock. So our boat is now that far away. Okay, so notice we use the law of cosines there rather than the law of sines, even though we could have done a little bit more legwork to find this angle and or this angle and done our law of sines as well. that gets us a look at the law of cosines on this particular problem. We have a couple more to go here. We've already talked about our bearing measured in a clockwise direction. That's used in aviation and also in navigation. So from a north line, 60 degrees, north line 90 degrees, north line 160 degrees, and so on. It's always measured from a north line in a clockwise direction to the point where we go all the way around. We go around 360 degrees. We're headed straight north. We're 360 degrees as our bearing. So that's already been explained before. Just a quick refresher course there. Radar beam detects an aircraft at a range of 20 miles and a bearing of 40 degrees. 30 seconds later, the radar detects the same aircraft crossing the 42-degree bearing from the radar site at a distance of 21 miles. What is the speed and direction of the aircraft? So from here, we'll make our radar site right here. We're at a bearing of 40 degrees. So from here, we're going to go in a clockwise direction about 40 degrees right here. And it says that we are 20 miles away. Our airplane is right here. 30 seconds later, the radar detects the same aircraft crossing the 42-degree bearing. So we're going to move a little bit to the right, and now our airplane is 21 miles away. And this entire angle here in red is 42 degrees. We want to find out the speed. We'll just do the speed of the aircraft for right now. Maybe come back to the direction. We'll have to wait and see. So notice we're trying to find that distance. If we find that distance, it's traveled that far in 30 seconds. Distance equals rate times time. So we could use that to find our speed or our rate. So I'll rewrite that as rate equals distance divided by time. We already have our time as being 30 seconds. So we'll come back and find our distance, or x, and plug that in there and get our speed, and maybe change that to a more manageable distance, such as miles per hour. Okay, so taking a look here, if this is 40 degrees and this is 42 degrees, the angle inside our triangle is 2 degrees. So once again, you should be able to note that we have two sides and the angle between those two, which allows us to use the law of cosines, or x squared equals 20 squared plus 21 squared minus 2 times 20 times 21 times the cosine of 2 degrees. And if we plug that in and take the square root of it, since we want to find x, we're going to get x to be about 1.23 miles. Now that we have that, I'm going to put that 1.23 miles in here. And I'm going to go 2 steps further, thinking back to our work in, I think, chapter 3. More manageable or more meaningful rate for us will be miles per hour. So I'm going to change my seconds over to hours. There are 60 seconds in a minute, and an hour is 60 minutes. So I've converted from seconds over to, put that last one upside down, just having a banner day so far. So let's try that again. I want to cancel my minutes, so I have 60 minutes over an hour, and that will cancel out our label of minutes as well and change it over to hours. And if we plug that in and do our calculations, 1.23 divided by 30 times 60 times 60, our speed is about 146 miles per hour. All right, we're going to try that again here in our next problem. And using our distance measuring equipment, a pilot determines when it passes a 90-degree radial from a navigational aid, the aircraft is 80 nautical miles away. 10 minutes later, as it crosses the 125-degree radial, the plane is 70 nautical miles away. What is the ground speed? And I think for now we're going to skip the course, much like we did in the last problem, the direction. We're just going to find that ground speed again. So from our navigational aid, we're from a north line in a clockwise direction. 90-degree radial would be straight out. When it crosses that, this is 90 degrees and make it a right angle, it is 80 miles away. 10 minutes later, it crosses a 125-degree radial, so I come past that. 125 degrees will be out in here. So the entire angle there is 125 degrees. It's now 70 miles away. We want to find the speed of our plane. So our plane has traveled from here to here in those 10 minutes. I've mentioned this was a right angle. This is 125 degrees, so 125 minus 90 is going to give me a 35-degree angle in here. And much like our last problem, to find x, we could say x squared equals 80 squared plus 70 squared minus 2 times 80 times 70 times the cosine of 35 degrees. If we plug that into our calculator, we're going to get x to be about 46.1 miles. So in our 10 minutes, our aircraft has traveled 46.1 miles. We're trying to find our rate. I'm going to put that back up here again. We've all seen this equation before. Distance over time. We have 46.1 miles as our distance. 10 minutes is our time. And much like our last one, let's make it more meaningful, making it miles per hour by converting our minutes over to hours. There's my unit conversion. Minutes cancel. And our rate is going to be about 276.6 miles per hour. So this airplane is going substantially faster than our last one. I think that does it. That does. That's our last word problem to give us an idea of what we're doing.